Hello everyone, here's a problem that's very typical for Chapter 7, Section 3. Let's walk through it together. Use the given information to find the number of degrees of freedom, the critical values of the left and right chi-squareds, the confidence interval estimate for sigma, the standard deviation. It is reasonable to assume that a simple random sample has been selected from a population with a normal distribution. And these are our two requirements. Has to be a simple random sample, has to be normal, or sample size has to be greater than 30. This is only 30. So if this population were not normal, we wouldn't be able to do this. But because it's normal, we can accept any sample size. What is our sample? Our sample is a bunch of cigarettes. And we're noticing the different quantities of nicotine in them. And for some strange reason, we want a 90% confidence interval. I don't think this is very standard. The degrees of freedom is a simple calculation. It's always sample size minus 1 for the chi-squared. So sample size is 30. You could use a calculator if you wanted to. You probably don't need it. Let's just say 30 minus 1 is 29. They seem to like me. To find the chi-squared L and chi-squared R values, go to stat, go to calculators, go to chi-squared, click on the between, and put in this confidence level, 90%. Degrees of freedom, we just found was 29, put that in first. Now here comes my 90%, 0.90, hit the compute, and I have a left and a right value for my chi-squared. And of course I have to round it. Here they want it to 3 decimal places. So chi-squared L will be 17.708. And chi-squared R will end up as 42.557. Now to find the confidence interval estimate, we use the variance stats tool. We have only one sample until we get to chapter 9. Here we only have a summary. They want to know the variance. This is where it starts to get tricky. They've given us this value of 0.24, and we're tempted to key this in. But remember, this S is a standard deviation. They want to know the variance. The variance is the square of the standard deviation. So go back to our calculator, put in the 0.24 that they've given us, press the square button, and it's 0.0576. If you're doing this online, you can use the copy, Control-C, and then paste, Control-V feature. If you're using a pocket calculator, just key it in. Sample size, they told us, was 30, so we put that in. Confidence interval, click the radio button to select it. They want 90%, so we change this 0.95 to 0.90. Press compute, and here we have our upper and lower limits. Great, that was easy, except that these are the wrong answers. The reason these are the wrong answers is that these are variances. We are finding the confidence interval for sigma. These are sigma squared. So what we have to do is take these values. I'm going to use copy and paste. Here's my copy, Control-C to put it in the clipboard. Go to my calculator, Control-V to paste it in. That's a sigma squared. If I press the square root button, I now have a sigma. And so I can round it to 2 decimal places as requested. 0.198 turns into 0.19. For the upper limit, I do the same sort of thing. I'm going to select it, Control-C to copy it back to the calculator, Control-V to paste it, take the square root. I get a long, long, long value, which I will summarize by rounding to 2 decimal places, 0.31. Don't like me. What did I do wrong? 0.19. 0.31, 29, 0.0576, 90. Huh. I hate messing them up. This one's wrong. This one's blue, so I can tell it's right. Why is this one wrong? Let's go back to the calculator and redo it. 0.03925,097 or something like that. Paste it in. Square root 0.198. Oh, if I round this to 2 decimals, it's 0.20. Sometimes I've said rounding is the hardest part in this class, and there's an example where I didn't look far enough ahead, and I rounded it wrong. Nice job, Gary. So here's a typical problem from 7.3 where they want to know how to calculate the sample size required to get a certain level of accuracy in a confidence interval for a standard deviation sigma. And if you remember in 7.1 and 7.2 when we talked about proportions and means, there were some formulas more or less complicated, and we used a tool instead. With standard deviations, it's actually a lot easier or a lot more complicated. It's complicated enough that we don't want to use any formula at all. It would be too much work. Well, that makes it easier because what they do is they create a table for us. So here's a sample. It's a simple random sample from a normally distributed population. So we're allowed to use these techniques. It's a bunch of IQ scores of statistics professors. I would like to say that statistics professors have high IQ scores, although I have no evidence for that. But it's nice to dream, right? What we want to get in this problem is the minimum sample size needed to be 99% confident that the standard deviation is within 1% of the population standard deviation. And so all we have to do is take this 99% and find it here. There's 99%. And we want to be within 1%. And so find the 1%. We need 33,218 statistics professors. We key that in, don't need to round anything. Well done. Is that sample size practical? That sounds like a lot. I don't know that many statistics professors myself. If you wanted to be, I mean, I know 14, I know 20 or 30. No, I'm going to say no because that's really, really large. It would be hard for me to find 33,000 statistics professors and then administer each of them a IQ test. So the use of the table makes this really, really easy. If I hadn't put all this extra verbiage in between, it takes about 20 seconds to actually work one of these problems. And I can kind of do whatever I want because I'm going to edit this later. I cut all this stuff out.